Hello, everyone. Today, I'm happy to share a tutorial that I prepared for monoplotting. My name is Roger Wang. I'm an assistant professor at the Department of Civil and Environmental Engineering, Rutgers University in New Jersey. I'm very honored to be selected as the EarthCube Learning Communities Fellow to present this tutorial for the community. And in the following 20 minutes, I would like to first introduce the technology of monoplotting. And then I will show you a short tutorial on how to use the tools to do monoplotting. And at last, I would like to share some of my personal perspectives on the future development of monoplotting technology. So as we know that visual data is very important. It has been it contains a very rich contents and also give us a very detailed information about the geoscience. For example, in the past, people have developed like photolithography to capture the landscapes in the past. One example is on the left upper corner. So you can see that people have used photolithography to capture the glacier in Switzerland. These kind of paintings are very accurate and could reflect the reality. Similarly, on the right-hand side, you can see two panels. The upper panel is a lithography panorama about a glacier. It was captured in 1842. At the same location and for the same area, people have taken a photo in 2004. So you can see the comparison between these two graphs. And you can see that how the glacier's distribution changed over the years. Similarly, after the photography technology is developed, people can use the cameras to capture the landscapes. One example is for Rocky Cliff Coast on the lower left corner. So this kind of visual data, especially for the historical views of the Earth's surface, could be very informative to analyze the long-term change of the Earth's surface processes. Not least, recently people have developed new technologies. So for example, people have used aerial photography to capture the landscapes. This includes the high altitude UAVs, fixed wings, airplanes, and also multi-rotor UAVs. Using this new technology, we can capture wide coverage and also high resolution images. Another example is the CCTV cameras. Now, especially in the urban area, we have a wide coverage of the Earth surface phenomenon. With the development of digital camera and smartphones, nowadays it's so easy to capture a phenomenon on the Earth's surface using accessible devices. So you can see we have a lot of new tools. This gives us the flexibility and also very wide coverage and high resolution of the Earth's surface processes. But one thing I would like to emphasize here is that these images are not always like the satellites or other scientific imagery. These images could be oblique and shooting from a different angle. Satellites always shooting from top. So the images could be has a higher quality and also have a fixed angle. The angle and the pose of the cameras for the new technologies usually are not certain. So there's a lot of uncertainties in capturing this data. So there are benefits and challenges to use this data. So as you can see that for some situations like in the past and for emergency situation like earthquake, dam break, landslide, probably the ancient data, like a photolithography and some old photos, they are the only data source that you can use to analyze the long-term process. And also for some situation, it's difficult to set up very strict and very strictly controlled imaging. So in that situation, people have to use the flexible angle and some improvised capturing situation. In that case, those visual data are very flexible to use to record the Earth's surface. And also because those data are very close, you can see that those images and videos are very close to our daily life. So it's easy to use these data to communicate with stakeholders. And also these data sources are compatible with the dynamic situation, which means they can capture like the moving objects and also changing objects using videos or using continuous capturing of the photos. But these data could be very challenging to analyze and extract valuable data from. For example, this data source usually has the oblique angle. So georeference the objects or the phenomenon or the processes in the videos in the 2D image could be very challenging. And also extracting the distorted view of the process and the objects could be challenging. Monoplotting could be a solution to those problems. So what's monoplotting? Monoplotting is a technology that you can use. You can identify a few ground control points on the 2D image and also in the 3D surface. And after giving the correlation between the ground control points, you can set up a few mathematical problems. Solving these problems will give you the position and the pose of the camera. And using this way, you have the information to project every pixel in the 2D image to the 3D world. Using this, you can georeference the data and also you can extract information in the 3D coordinates, which will be very valuable for geoscience community. Monoplotting has been developed for a while. Here is a short history of this technology and the associated tools. So monoplotting is originally named and invented in the 1970s by Makarovich. So it has been used to transform photographs into georeferenced data. Since the pioneering work in 1970s and the 1980s, several efforts have been made to develop software and tools for monoplotting oblique pictures. Here I'm listing some of them, and you can see that people are still actively developing new tools in this field. And also some of the tools have a very user-friendly interface. So that help the users to learn this technology and use this technology. Monoplotting has been used for quantitative analysis of natural hazards, glacier process, land cover changes. And hopefully after the tutorial, users like you could find other more interesting, more inspiring application of those using those tools. So in the following, I will introduce one tool called the Pick2Map. This this tool is a plugin for QGIS. So if you have a QGIS, you can install this tool. And in the following a few minutes, I will show you how to do this and how to convincingly and reliably use this tool. Okay, so then let's talk about the Pick2Map. Pick2Map is a plugin for GitHub for QGIS. So it has been originally developed in this thesis, Galen Milani's master thesis at EPFL. And it has been contributed by others. And now it's a plugin for QGIS, and it has been tested with QGIS 3.12. And installing the plugin is quite straightforward. So next, let me show you how to do so. First, open QGIS desktop. And then you can go to plugins, manage and install plugins. Now you can go to settings, show also experimental plugins. Check the box. And now go back to all. And you can search here, Pick2Map, and just check the box, close it. Now, if you click the plugin tab again, you can see Pick2Map is there. Well, sometimes some computers still need some dependencies. For example, OpenGL and PyExif. So if you had a problem with these things, please follow instruction on the web page to install the plugin. And there also, I find very helpful if you have some issues. The issue has the threads. If you follow those things, I think these are very helpful. For example, for Mac computer, how you install those dependencies. You can access the information here. Okay, let's go back to the QGIS. Once we have this, their website also provides an example. So you can use the example here. If you go to Pick2Map, data test, so you have two files to download. One is this GPG file, and another is this DEM file in the extension of a TIFF. Okay, you can download these files, and I'm going to use these two files to demonstrate how to use the Pick2Map plugin. Okay, so this is the QGIS interface. The first step, we can add a layer of the DEM. So I will follow the instruction here. And if you have downloaded that, go to the folder, select the Glacier DEM.tiff, add that layer. Okay, so now we have the DEM information for this. All right, so you can see this is a mountain area, and we have different peaks. So now the task is to monoplot picture. So we are going to choose this JPG file, open that. In the input elevation model, you can either add selected DEM, which is what we already opened in QGIS, or you can choose import DEM from other from the directory, from the system. Okay, after that, click OK. Then the pick-to-map interface will open. And I suggest you put the windows side by side. In this way, we can better organize our ground control points selection. Okay, if this is done, we can take a look of the first step to do monoplotting is to identify a series of ground control points. To do this, we have this button here. Click this button. So there's a ground control point 1. It's shown up here. Make sure you can make sure that the first row is also appeared on this GCP table. And then we can select one point. So the idea is that you choose the clear features in the DEM and also in the photo, and you can correspond them one-to-one. So in that way, you can identify the camera position and the pose. So we would choose the one is at the foot of the mountain. And I feel that the position is around here. Well, it'd be better if you choose the points very accurate. And you should have some sense that where this general photo about. So here you can see this is like a basin, and it's actually about this basin. So you need some background knowledge about this photo to really perform the monoplotting. And we identify that this area is actually what this photo about. So the first thing, we identify the first ground control point, and then we add another one, which is at the mouth of this basin, and it's probably at this location. And then you can add the third one. We would like to choose this mountain top, the peak of the mountain, and then we will choose here. It's very likely to be here. And then number 4, we are going to choose this most obvious point, which is at the top of the peak. And in the DEM, it's at this location. So keep doing this. For example, number 5, we are going to choose this point. And it's likely to be this one. Number 6, we choose this. It looks like a very obvious point in the photo, and we can choose, looks like here in the DEM. And the number 7, it's we would like to choose this peak, and it's likely to be here. And the number 8 looks like very far away, and I would like to choose, maybe that's the peak somewhere here. Number 8, number 9. Okay, that's probably somewhere. This is another peak. I guess it's around there. So it's okay if your points are not accurate. You can also adjust it by click other points. You just to select. For example, if we want to change the number 8, we can go to number 8, the row, highlight number 8. So we can either click here or click there to make some adjustment. Okay, after you selected those ground control points, you can click this button to estimate the position of the camera. And now, if you allow all the parameters to be free, for example, X, Y, Z positions, the tilt angle, the heading angle, swing angle, and the focal length. If you allow free parameter optimization, so you can just use this estimate. Well, the system tells you that there's some inconsistent pose because it cannot match. So in this case, we have a general sense that the gentlemen are standing and sitting on this side of the channel. So it's probably somewhere here. So it's better to know the coordinate around here to have some idea to better optimize this. So we guess it's around here. So let's we can check the coordinate. You see that the coordinate points are shown here. So if the mouse is moved over this point, you can see 650,599. So you need to remember that. We can 650,599. Oops. We can enter here. Select the priority, and we can choose 650. 650. 650, 495, 495. Okay, and the Y position, if we want to select that as well, 142357. 142357. Okay, so if given this priority determination, and see whether we can improve that. Still, there's some inconsistent. Okay, at this stage, we will just use fixed. So again, it's 650,521, 650,521, and 142253, 142253. So using this way, we force the camera's position at this location. Okay, still not quite converging yet. I'll try that again. Okay, in that case, we are going to so let's see the height of this location. The height of this location is about 2725. So we are going to enter the height. Okay, still inconsistent. We need to change that a little bit back to the a priori. I think there probably a problem for 0.8, so I will just delete 0.8 here using this button. Okay. Now let's estimate the position again. Okay, now we have some better success for this. Looks like the position is improved, and the looks not bad, which is very close to what we want the position of the camera. And if you check the comparison of the ground control points. Looks like all right. They have to some extent match. Well, other suggestion to improve the convergence is to double check the values here and try to improve the accuracy and the correspondence of those points. Okay, for the interest of time, we don't have much to improve here, so I will just stop here. You can save the ground control points by using these buttons and also load some ground control points before. And also you can do other things. But the next, the most important step is to using this 3D view, you can check whether how it looks like in 3D. And it looks like a little bit blocked by the mountain front. And we can go to this monoplotter to see how it looks like. And here, the first thing to check is the DEM transparency. So we can show the DEM here and see whether they have a good match. So maybe the camera position is not perfect, but if you, the camera is about, it's behind a big stone here. But if you look at the DEM, it looks like they have a fairly good comparison between the two images. If we make it semi-transparent, they almost overlap. So that tells us, okay, it looks like we have some good matching between the two, the DEM and the photo. Okay, after that, we almost know the coordinate of every pixel in this photo. So to save that, we can save XYZ matrix. So each TIF file will save the coordinate of the every pixel here. So that's kind of helpful. You can also measure on the 3D. So for example, you want to measure how long if you walk from here to here and here, following the foot of the mountain. So it gives you the distance by meters. Okay. There's also other useful information, like you can create also rectification map. You can save that for your review. And you can also save the image if you want to have a semi-transparent. So you can save the image to show how good the matching is. Other useful information is the geometry analysis. Using this, you can estimate like how large. So you can see the area of the pixel and how each pixel, if you project the pixel into the real 3D world, how large area each pixel takes, and what's the angle between the ray and the DEM. So there will be interesting, calculations that you can make. All right, I think that's the end of this operation of the QGIS plugin. So I will stop there and allow you to explore the other functions of this plugin. And most important is to make sure your ground control points are enough. So at least I believe it depends on how many free parameters you want to obtain. So I suggest you need to have more ground control points to make a more accurate monoplotting. All right, so that's all I want to say for this part. Next, I will share some my personal perspective on the future of this monoplotting technology. So next, let's talk about some applications that has been conducted in our lab. And also, I would like to share my views on the future development of monoplotting technology. Here is the first example. This is an emergency issue about the dam break in Edenville, 2020. So during that dam break event, um, a, a local resident used the smartphone to capture the video of the dam failure process. And this is the only evidence capturing the whole process on the field. And you can see that this is some frame extraction from the video, and the dam start to break from this point. This is a 2D video, and extracting and georeferencing such a video is very challenging using traditional method. So we use monoplotting that we can identify the DEM, and here is the comparison between DEM and the dam break. And we can apply optical flow, which is a particle tracking method, to follow the dam collapse. And you can see the some materials, how they move during this process, and the numbers here are the velocity of each material point. We can also using the information obtained from this video to reconstruct the failure process. Another example I would like to share with you is the urban flooding. So you can see we use a camera to capture the water accumulation in a parking lot. And due to the lighting and the background change, you can see that it's very challenging to estimate the flooding extent change over time. We developed a semi-supervised water extent identification algorithm, and we can reliably identify the boundary of the flooding water ponds there. And using monoplotting, we can identify the location of the camera, which is these yellow points. And these white points are the corresponding ground control points. Using this monoplotting method, we can project this identify the boundary of the flood extent to the map. So you can see the black areas are those water areas, and you can see this from this oblique image. We can at last obtain the full distribution in the georeference data at last. In the future, I think monoplotting hasn't been applied a lot in these areas, but I feel there's a great potential to apply it to analyze the wetlands, the forest, the vegetation distribution over the land, and also the glaciers, which is relatively more common in monoplotting. I think this is a quite interesting field to explore. And in our lab, we still developing new methodology. So as you have seen in the tutorial, identifying those ground control points is very challenging, and it needs a lot of labor and very time consuming, and relatively you need to use a lot of time and iterations to find the best matching points. So our idea is that we can use computer that automatically identify some very clear features, very obvious points the computer can recommend or automatically capture those points, and then humans can select those most interested points for the monoplotting. Similarly, the ground control points can be obtained from the DEM data as using some computer vision method. So we are trying to automate this process. And so far we have got very positive results, and we have submitted a paper about this method. And in the future, we would like to see, we would like to develop a new method that everything could be fully automatic, or at least could be semi-automatic, that human have very limited burden to do the monoplotting task. Okay, at last, I would like to thank my collaborators, including Dr. Yixing Yuan, my student Bazat, Gopava, David Bazat, and I really appreciate the organization by the EarthCube Learning Community Committee, and at last, the funding sources for my research, the Rutgers University EOAS and the Research Council seeding grants, which allow this, which allow us to perform this very exciting new research. Thank you.